this evening we are going to be talking about the motion of a box on an inclined plane. Now this is one of the typical problems which you will find in first year physics and also which is found in everyday life. So it is very, very important that you have an understanding of what is going to happen when you are on an incline. Okay, when things are moving on an incline, what is it that is going to happen? Okay, just a minute. Like I was saying, the movement of a box on an incline is a very interesting physics problem, and it is important that you understand what is going to happen to an object when it's moving on an incline, and that's what we want to look at. The first thing we want to look at is what is an incline. So basically, an incline is a surface which is tilted at an angle. Okay, so with a flat surface like the previous case, but this surface is tilted at an angle like this. So this is our surface here, and this is what we call an incline. I'm saying that an incline is a surface which is tilted at an angle. So as you can see in this diagram, so you have this particular surface here, the hypotenuse, and this hypotenuse is tilted at an angle like this. So this is what we consider to be an incline. So when we are talking about the motion of an object on an incline, we want to study the movement or the motion of an object on a surface like this. Okay, so that's what we want to do. And usually the angle of the incline is an angle which is less than 90 degrees. So you can have so basically typically our angles are much less than 90 degrees when it comes to inclines. So what is it we want to do? So basically what we want to do is we want to study the motion of this box. So as you can see in this diagram, we've got an incline which makes an angle of theta here. So the angle of the incline is theta, and on this incline there is a box which has been put there, and the mass of the box is m. Now one of two things are going to happen with this box. Either this box will choose to remain on the incline, so it does not move and it stays there on the incline, or this box will choose to move downwards. Typically when you have this kind of a situation, it's very rare that actually it doesn't happen that the box on its own decides to move up, unless you are pulling the box or you're pushing the box upwards. So if you're pulling the box upwards or you're pushing it upwards, then it can move upwards, but on its own the box will most likely choose to do one of two things. Either it will stay where it is right here, or
try to fix your network, otherwise we're not getting anything.
I have internet. So is it everyone who is not hearing anything?
Yes, sir, yes. We are getting you.
Some people are getting me, other people are not getting me. So don't accuse me of not having fixing network things. There's nothing wrong with my network. So if it's not everyone who is having the same problem, then it's not my network. Okay. So one of two things can happen, as I've said. Either the mass can remain or can choose to remain motionless. So when the mass remains motionless, as we know, an object which is at rest or is motionless has an acceleration which is equals to 0. The other case is when the object, this particular mass, chooses to slide down the incline. Now, when this object slides down the incline, like any of you, I think if you have had the pleasure or the opportunity to go down an incline like that, you will find that if your velocity or whatever object is going down an incline will start moving faster and faster and faster and faster, even if you're not doing anything. Okay? So the fact that this particular object or this mass is going to move faster and faster, meaning that the velocity of this object is going to increase as it goes down the incline tells you that there is acceleration which is present. How do you know that there is acceleration present? It is because the velocity of the mass is increasing. So as any object goes down an incline, its velocity increases if nothing else is being done about this. So we have two cases here. There is a case when the mass remains motionless, where the acceleration is equal to 0. There is also the case when the velocity of the mass changes. So we know that in that case, the acceleration is not equal to 0. Are we clear? So when the mass remains motionless, we know that the acceleration is equal to 0. And when the velocity of the mass as it goes down increases, in that case, we know that the acceleration is not equal to 0. So we've got two situations: when the acceleration is equal to 0 and when the acceleration is not equal to 0. Is that clear?
Yes, sir.
Now, if you have a situation where at one point this particular object chooses to say, I'm not going to move, therefore acceleration is equal to 0, the other point it can slide down the incline and its velocity increases, then the acceleration is not equal to 0, then it tells you that according to Newton's second law of motion, F equals to ma. This particular box has got a mass. If it chooses to not move, then the A is equal to 0. If it chooses to move, then the A is not equal to 0. Then it tells you that there is a resultant force. At one point, when it's moving, with acceleration not equal to 0, there is a resultant force which is not equal to 0. At the other point, when this box decides to stay motionless, the resultant force acting on this box is equal to 0. That is the only conclusion you can make, because at one point this box is motionless, meaning that the acceleration is equal to 0. The other point, this box can move with increasing velocity, meaning that the acceleration is not equal to 0. The only reason why that is happening is because when the acceleration is equal to 0, according to Newton's second law of motion, the resultant force acting on the box along this direction is equal to 0 at that point. And when the box is moving or sliding down the incline, as it slides down the incline with increasing velocity, at that particular time when that is happening, it tells you that the resultant force is not equal to 0 and it is positive. That's why the velocities are increasing. So you have two situations where at one point the resultant force is equal to 0, at another point the resultant force is not equal to 0. Are we clear?
Yes, sir.
Yes, that is the only, those are Newton's second law of motion is the only thing we have to explain what's happening. Okay, so if this thing of when this thing is moving, it's because there is a resultant force which is positive and not equal to 0, and when it's motionless, there is a resultant force. This thing, therefore, forces us to find what this resultant force is. We need to find the resultant force, which is causing this object to remain motionless. We need to find the resultant force, which is causing this object to slide. Acceleration is the result of resultant force. Are we clear?
Yes, sir.
Yes. So if acceleration is a result of resultant force, and we know that resultant force is a vector, that's the other thing. A resultant force is actually a vector you obtain by adding a bunch of forces. So for us to work out the resultant force, we need to know, or we need to come up with directions. Which direction is going to be the x-axis? Which direction is going to be the y-axis? That's what we need to do. Otherwise, we are not going to be able to work out any resultant force if you do not know the direction. So you need to be able to find directions. which direction will be the x-axis of this incline, which direction is going to be the y-axis. Okay. So, in our case here on this incline, we choose the direction parallel to the incline. This direction which is parallel to the incline. So we choose the direction parallel to the incline to be the horizontal direction or to be the x-axis. So the direction on this incline parallel to the incline, that is what we choose to be the x-axis. So any direction parallel to the incline, we choose that as our x-axis. If that is our x-axis, we know that the x and y components axis are at 90 degrees to each other. If we choose the direction parallel to the incline to be the x-axis, then we can choose the direction perpendicular to the incline at 90 degrees to the incline. That is going to be our y-axis. So we have done a bit. We have chosen which one is going to be our x-axis. We have chosen which one is going to be our y-axis. So we're saying parallel to the incline, this is going to be our x-axis. Perpendicular to the incline, which is at 90 degrees to the incline, this is what's going to be the y-axis. So that's the first thing. But that is not enough for us to find a resultant, because resultant forces depend on direction. So simply choosing an x-axis to be parallel to the incline and choosing a y-axis to be perpendicular to the incline is not sufficient. We need to choose which of these directions along the x-axis is going to be the positive x-axis and which one is going to be the negative x-axis. So in a case like this, when you have an object which is going to move and maybe its velocity is going to increase, basically it's sufficient to choose the direction in which the object is going to move as the positive x-axis. So in this case, on this incline, since our object most likely when it slides on its own is going to slide downwards, we choose the downward direction in which the object is going to slide to be our positive x-axis. So downwards along this direction, we choose that to be our positive x-axis. Then if that is our positive x, so coming down this way, if that's our positive x-axis, it means going up is going to be our negative x-axis. So we take care of which part of this x-axis is positive and which part of the x-axis is going to be negative. So down here, we choose this to be our positive x-axis, meaning up there is going to be our negative x-axis. Similarly, along the y-axis, right now we don't know which part is positive and which part is negative. So we choose the part of the y-axis above the incline to be our positive y-axis, and we choose the part of the incline or the y-axis below the incline to be our negative y-axis. So the part of the axis above the incline is going to be the positive y-axis, and the part below the incline is going to be our negative y-axis. So with this discussion, we have come up with something in terms of direction which we can use to work out resultant vectors. So in this case, along the incline, that is our x-axis. Down this incline, that is a positive x-axis. Above the incline, negative x-axis. Up there, negative x-axis. Perpendicular to the incline, above the incline, that is your positive y-axis. Below the incline, that's a negative y-axis. Now, with such a xy plane lying on this incline, it will become clear that this mass, this object, which has got mass, if an object has got mass, we know that that object also has got a force acting on it as a result of the mass which it has. The force which is acting on the object as a result of the mass, that is what we call the weight of the object, which is mg here. So in this case, you can see there is this vector from the box acting downwards and pointing straight down like that. That is the mg. That is the weight of the object. So that is the weight of the object here. So that is the weight of the object here. Okay. So this weight of the object is there acting on this particular thing, this particular box. So there is a force called weight which is acting on this box, and that weight points downwards. Are we clear on the weight that is pointing downwards?
Yes, sir. We are clear.
The next force, which is there, which has not been shown right now, is something called friction. Now, friction is always present, whether the object is moving or the object is motionless. If this particular object remains motionless, it does not mean that there is no friction. Friction is there. The kind of friction between the incline and the box which is going to be there when this object decides to remain motionless is something called static friction force. If this particular object decides to slide down the incline, there is also going to be another kind of friction which is going to be acting between the incline and the object, and that is what is called the kinetic friction force. So whether the object remains motionless or the object slides down the incline, there is always friction present between the box and the incline. So there is another force called friction acting on this box which has not been shown and which is going to be shown very shortly. Since the box would naturally tend to go down, slide down, it means that the friction force which opposes the motion of the box as it is going down will have to point up this way. Are we clear? The friction force will have to point up the incline since the box will naturally tend to move down this way. Is that argument clear?
Yes, sir. Yes, sir.
Yes, the friction force always opposes the movement of an object. So since our object will slide downwards, as it will always be the tendency for it to do, then the friction force has to point up like that. Okay. So that being the case, they are, as things are right now, there are two forces acting on this box. There is friction, which is pointing upwards, and there is this weight, mg, which is pointing downwards like this. So there's friction pointing up the incline, and there's weight which is pointing down the incline like this. Okay. Now, the thing is, when you look at this weight which is pointing down the incline, and the choices we have made about which part is the x-axis and which part is the y-axis, we have said the x-axis is parallel to the incline. That's what x-axis is. And the y-axis is at 90 degrees to the incline, perpendicular to the incline. So if you have such a case of xy plane, then you notice that this force mg lies neither along the x-axis nor along the y-axis. Is that clear? If we have made this choice of saying x-axis is parallel to this line, to this incline, and y-axis is perpendicular to this line, then you notice that this weight does not lie along the x-axis, and it also does not lie along the y-axis, which is this weight. So if we have a weight which does not lie along the x-axis and doesn't lie along the y-axis, then we are obliged to find out how much of this weight lies along the x-axis and how much of this weight lies along the y-axis. The how much of the weight lies along the x-axis, that is going to be the x component of the weight. The how much of this weight lies along the y-axis, that is going to be the y component of the weight. Are we clear? So we need to find out how much of this weight mg lies along our x-axis and how much of this weight mg lies along our y-axis. Are we clear? So that's the task which is at hand. Yes, that's a task which is at hand. So, with this question of how much of this weight is lying along the x-axis and how much of this weight is lying along the y-axis, it becomes clear that you need to find out how much of mg lies along this line and how much of mg lies is this much here. Now the lucky bit in this case, due to geometry, is that this angle between mg and the y-axis, you've seen this angle, mg and the y-axis, this angle is also equals to theta, which is the angle of the incline. So this angle between the weight and the y-axis, this angle between the weight and the y-axis, this angle is equals to theta. This angle here, as indicated here. So this angle is also equals to theta as indicated like that. Is this clear?
Yes,
So,
it is clear.
so if this angle is equals to theta, then you know how much mg is, then you can find how much this y component is. This component which lies along the y-axis. So mg, that, if this is theta, then you can find out how much the adjacent is here. So the adjacent is going to be equals to what we have here, mg cos theta. And you can find out what the opposite this side is going to be. The opposite is going to be mg sin theta. So this adjacent, which is mg cos theta, this is your y component of the weight. As you can see, the adjacent lies along the y-axis. So this is your y component. So on an incline, your y component is mg cos theta, the y component of the weight. This one here, which is the opposite of this triangle, this is your x component, mg sin theta. Why do we say it's an x component? Because the direction of this component, as you can see, the dotted line and the angle, this component is parallel to the incline. So the direction is the same as the direction of the incline. So we can pick, since the direction is the same, we can pick this component, we can put it up here as shown in our next diagram. So this one here, mg sin theta, is your x component of the weight, and this component here, mg cos theta, is your y component of the weight. So we can lift this one, mg sin theta, we can bring it up there. When we do that, we have not changed anything as shown in this diagram here. So we lift it and we bring it there. Mg sin theta, then of course this is what the weight was, and this is the mg cos theta, like that. Now the other thing which is going to happen is that, before I go to the other thing which is going to happen, this mg sin theta, this is the part of the weight which tends to pull the box down. That is why your box always tends to move down. It is because of this part, mg sin theta. Mg sin theta is the part of the weight, or is the component of the weight which pulls the box downwards. And why does a box always tend to move downwards? It tends to move downwards because usually friction is, most of the cases, friction is much smaller than this mg sin theta. So if mg sin theta is greater than the friction, then the box will be pulled downwards. That's why your box always tends to move down. It's because there is a part of the weight, mg sin theta, which is greater than the friction pulling the box down. That's why your box, if you put it on an incline, it's either it remains there. When it remains there, it means that mg sin theta is equal to your friction. But if mg sin theta on that particular case is not equal to your friction, then your box is going to slide. It will be pulled by this guy, mg sin theta, downwards. Are we clear? Are we clear on this case? So mg sin theta is a component of the weight that pulls the box down. Apart from this component of the weight pulling the box down, there is also another component of the weight, which is the y component, mg cos theta. This mg cos theta exerts a force on the incline along this direction, along our chosen y direction. So mg cos theta exerts a force on the incline, directly on the incline. The incline is not going to be happy according to Newton's third law of motion. If you exert a force on a particular surface, that particular surface is going to push back against you. So this box is exerting a force along the y-axis equals to mg cos theta. The incline will feel this force. It's not going to be happy about this. So the incline is going to push back against the box along the y-axis with an equal but opposite force, which is called the normal force. This one here. So the normal force is the result of the incline pushing back against the y component of the weight, which is mg cos theta. So as you can see, we have broken down our weight, which is mg, into two forces. The one along the x-axis, which is mg sin theta, and the other one along the y-axis, which is mg cos theta. This force, mg sin theta, is the one which tends to pull the box downwards. This force, mg cos theta, is the one which tends to exert a force directly on the ground, on the incline. The incline is not happy about this, so the incline pushes back with the normal force F here, Fn, there. Since the box is being pulled downward by this force mg sin theta, there is going to be friction, which is going to oppose this movement of the box downwards, which is this friction force here. So depending on whether the box moves, if the box stays motionless, then the friction in this case is static friction force. If the box moves with increasing velocity, then the friction in this case is what is referred to as kinetic friction force. So with this setup, it is possible for us to now work out the resultant forces. Okay? Because for us to work out resultant forces, we need to identify which forces are acting along the y direction, which forces are acting along the x direction. In our case, the forces acting along the y direction is the normal force, which is this one, and mg cos theta. The normal force is pointing above the incline, is acting in the direction above the incline, so the normal force in this case is positive. This mg cos theta is acting in a direction which is below the incline, so this mg cos theta is a negative force. This mg sin theta is pointing downwards, dragging the box downwards, and this is the direction we have chosen to be our positive x direction. So this force, mg sin theta, is a positive force. This friction force is acting in a direction which is opposite to our positive x-axis. So this friction force is a negative force. So we have actually accomplished a lot by assigning to this incline precise directions, and also by identifying which forces on this diagram are acting along the x-axis and which forces are acting along the y-axis. So we start our calculation of a resultant with the y-axis. Why do we start with the y-axis? It is very simple, because the only thing the box does is it moves along the incline. It doesn't go up or down the incline. It just slides along the incline. It's either it's going to remain motionless on the incline, or it's just going to slide. But it's not going to jump like a projectile and come down. That's not going to happen. So if the box is just moving along the x-axis, then there is no acceleration along the y-axis. So that is a very simple case. So we know that along the y-axis there is no acceleration. At the same time, we know the forces which are acting along the y-axis. It's the normal force and this mg cos theta. So we can work out the resultant force along the y-axis. So the resultant force here along the y-axis is going to be equals to the normal force plus the y component of the weight, which is mg cos theta. But since the y component is pointing down, we give it a negative here. So we end up having the resultant force equals to the normal force minus mg cos theta. So this is our resultant force along the y direction. Are we clear?
Yes, sir. Yes, sir.
So we know the resultant force. Once you have resultant force, and what's the point of working out resultant force? It's because you want to apply Newton's second law of motion. This one. The resultant force along the y direction is equal to the mass multiplied by the acceleration along the y direction. So in our case, the acceleration along the y direction is 0. So when you put your 0 here, multiplied by the mass, you get a 0 this side. So you end up having mass multiplied by 0 acceleration, you get a 0 this side. This resultant force, we replace it with this, the normal force minus mg cos theta. This is what you end up with. You end up with Fn minus mg cos theta, which is this side. So Fn minus mg cos theta equals to 0. So it means that you can get this, take it to the other side. When you take that to the other side, you end up having Fn is equals to mg cos theta like this. So what this is telling you is that the normal force, the reaction of the incline, as the incline is pushing back against a box, the normal force of the incline is equals to the y component of the weight, which is the mg cos theta. So always on an incline, this is how you get your normal force. Your normal force is equals to the y component, the weight, multiplied by cos theta, which is just the y component of the weight. So with that, for the y direction, there's nothing much we can do. We move on to the x direction. Along the x direction, there is this force mg sin theta pointing down. There is a friction force pointing up. Since this mg cos sin theta is pointing down, and down here we have said it's going to be positive, and up there we have said it's going to be negative. Therefore, our resultant force along the x direction is going to be equals to mg sin theta plus minus the friction force. So in that case, the plus and the minus, you end up having the resultant force being equals to mg sin theta minus friction force. So this is how you get your resultant force along the x direction. The other thing you're supposed to be aware of is that friction, this friction force, friction is always equals to the coefficient of friction, whether this coefficient of friction is a static coefficient or the kinetic friction. But the point is, friction is always equals to the coefficient of friction multiplied by the normal force. That's the thing. Friction is always equal to the coefficient of friction multiplied by the normal force. So we get this expression of friction here, we replace it here. So when you do that, we end up having the resultant force along the x direction equals to mg sin theta minus the coefficient of friction multiplied by the normal force. So this is our expression of resultant force along the x direction. It is equals to the component of the weight pulling the box down minus the friction force. Okay, so there are two things which can happen, as I've said. The first case we are going to look at is when the box decides to say, I'm not going to move. So the box remains motionless. When the box remains motionless, we know that in that case, the acceleration is going to be equals to 0. So we have the resultant force, then we have an acceleration which is equals to 0 because the box has decided that I'm not going to move. So we write Newton's second law of motion. The resultant force is equals to the mass multiplied by the acceleration. So our resultant force here is this whole expression here. This is our resultant force. Then our acceleration is equals to 0. And in this case, our box has said, I'm not going to move. So the kind of friction we are talking about is now static friction. If your box decides not to move, then the friction is going to be static friction. So in that case, whatever the resultant force is equals to, we'll get to it, equals to the mass then multiplied by the acceleration, because our box has said I'm not going to move, and this is going to give us a 0. So this mass times acceleration part will give you a 0 because the acceleration is 0. The reason why the acceleration is 0 is because the box has said it won't move. Okay, our resultant force is this here, mg sin theta minus mu k Fn. Since our thing is not moving, then we're talking about static friction. So this is what we end up having mg sin theta minus mu s, which is the coefficient of static friction, multiplied by the normal force equals to 0. Then there's a minus this side and the 0 that side, so we get this bit, we take it to the other side, so we end up having mg sine theta equals to static friction force. So if your box decides to say, I won't move, the reason why the box is not moving, it is because this mg sine theta here, mg sine theta is equals to the friction force. And since the box is not moving, the friction we are talking about is the static friction force. So if the box remains motionless, it is because this mg sine theta is equals to the friction force, and that is what this thing is telling us here. Equation 13, that if the box decides not to move, then the component of the weight pulling the box down is equals to the static friction force. Okay. However, we can do more, because remember, there is Fn here, and we have an expression of Fn already found, which is this one. Fn is equals to mg cos theta. There. Fn equals to mg cos theta. There. So in that case, if you substitute for Fn here, you end up having mg sin theta equals to mu s, which is the coefficient of static friction, multiplied by mg cos theta, like that. If you divide on both sides by mg cos theta, you end up having mu s is equals to mg sin theta divided by mg cos theta, which is going to give you sin theta, divided by cos theta, which is going to give you the coefficient of static friction equals to tan theta. Okay, so the coefficient of static friction in this case is just going to be the tangent of the angle of the incline. The theta is the angle of the incline. So that's how you find this coefficient of static friction. So if someone asks you to say, find the coefficient of static friction when an object is motionless on an incline, the way you find this coefficient of static friction is simply by working out the tangent of the angle of the incline. Any questions?
So I have a question. Huh?
Yes.
Sir, on the where is where down?
On the what?
Yes, sir. As in, sir, you said that we choose the where, as in the box is heading down to be the positive x-axis.
Yes.
What if negative x-axis? Does it have any effect to the answer?
You can choose whatever you want.
Okay. So you can choose it to be negative or positive?
No, you see, you can choose whatever. It's up to you to choose direction. Okay. The issue here is down the incline when your box, you see, when your box is moving down the incline, the velocity is increasing. Excuse me, just a bit. What is it?
No, she's being taken by her sister.
Oh. Okay, so when the box is moving down the incline, the velocity is increasing. Okay? So it's just natural that you choose the direction in which the velocity is increasing to be positive, because when the velocity is increasing, it means that the acceleration is positive. Are we clear?
Sir.
Yes.
Sir, as in, I was saying that what if you choose it to be negative? Does it have any effect to the answer?
When you choose the thing, if you choose it to be negative, it's going to be very difficult to interpret what's happening. It will be difficult to interpret what's happening, because how are you going to interpret the fact that down is negative but the velocity is increasing?
The way I'm going to interpret it, using the velocity time graph.
Using the what?
It's coming down to be negative. Velocity time graph. When something which is going down, the acceleration.
No. There is no graph here, Anga. There is no graph here. This is a slope. This is not a graph. If you think this is a graph, it's not a graph.
Okay.
This is a slope. It is like these Mshelemuko bridges we have in Lusaka, these flyover bridges.
Thank you, sir.
Okay, it's like the flyover bridge, Anga. So you can't put a graph on that flyover bridge. Say, no, it's a graph. No. You're not going to interpret it like that. You just be misleading people. Are we clear?
Okay, thank you, sir.
Yes. Any other question?
Sir, I've got a question.
Yes.
You talked of how to calculate
Yes, sir.
the static kinetic frequency.
Static what?
Static kinetic coefficients of kinetic frequency.
Coefficient of static friction.
Yes, please.
Yes.
How do we calculate the other one, the other friction, the kinetic?
The kinetic one. How do you calculate the kinetic one?
Yes, please.
Usually the kinetic one is calculated by moving the object. When you are pulling the object, okay? You pull an object. Are we clear?
Yes, please.
So you apply a non-pulling force, but you make sure that the object is moving at constant velocity. Okay? So let's say you're on a flat surface. Then you are pulling something with a known force, but you make sure that this particular object is moving at constant velocity. So if the object is moving at constant velocity, then your pulling force is going to be equal to the friction force. Are we clear?
Yes, please.
So if your pulling force is equal to the friction force, you know what you know the force with which you are pulling. So that part is known. Then this pulling force is equal to the friction force. The friction which the mass has when it is moving at constant velocity, when it's in motion. Okay? So this friction is the kinetic friction force. The kinetic friction force is going to be equal to the coefficient of kinetic friction multiplied by the normal force. But if you are on a flat surface, the normal force is equal to the weight of the box. So therefore, it becomes possible for you to find out what the mass is. You just divide your pulling force divided by the weight of the box. So basically, how do you find the coefficient of kinetic friction? You pull a box with a known amount of force, but you make sure that this box is moving at constant velocity. That the constant velocity part ensures that there is no acceleration. Are we clear? So this part, there's going to be no acceleration. If there is no acceleration, you multiply the mass times zero acceleration, you get zero. But on this other side, the resultant force is going to be equal to the pulling force minus the friction force. So this pulling force minus friction force is going to be equal to zero, because this other part side is going to be zero. Okay, then your friction force is equal to the coefficient of friction multiplied by the normal force. So your pulling force is going to be equal to the coefficient of friction, mu k, multiplied by the normal force. The normal force is equal to the weight of the box. So you just divide the pulling force divided by the normal force, and the normal force is the weight of the box. So it's basically your pulling force divided by the weight of the box. That's what's going to give you the coefficient of kinetic friction. Yes. Any other question? Before we move forward? Okay. So if there are no other questions,
So, sir,
yes.
is there any coefficients of static friction apart from kinetic?
The coefficient of kinetic friction, static friction. There's coefficient of static friction which you find by this, in this case, tan theta. There's also coefficient of static friction. Oh, sorry, kinetic friction. Usually coefficients of static friction are much larger than coefficients of kinetic friction. Coefficient of static friction are typically around 0.7, 0.75, 0.8, 0.85, 0.9, somewhere there. The coefficients of kinetic friction is much smaller, 1.5, 2.0, 0.2, 0.25, 0.3 there. Those are the values of coefficient of kinetic friction. So,
Alright, sir, thank you.
yes. Any other questions?
Other question, sir.
Yes.
Yes, there's a question.
Go ahead.
How did you come up with the equation for how did you come up with the equation for tan theta for static, yes, static friction tan theta?
Here it is. It's this. Because your object is motionless,
Hello.
here, because your object is not moving,
Yes.
there is zero acceleration. So you multiply the mass. This is Newton's second law of motion. You multiply the mass of the object times the acceleration, you get a zero. This is on the other side of the equation, mass times acceleration, that gives you zero. But we have just worked out here that the resultant force along the x direction is equal to mg sin theta minus the coefficient of friction multiplied by the normal force, which is that. Then that's what you've put here, mg sin theta minus, since our box has decided not to move, therefore the friction which is acting on it is static friction, the coefficient of static friction multiplied by the normal force, which is equal to that, which is equal to 0. So I get this part, I take it to the other side, I end up having mg sin theta equals to the coefficient of static friction multiplied by the normal force. But I've already found an expression of normal force at the beginning here. The normal force, Fn, is equals to mg cos theta. So I substitute that here. When I substitute that here, I end up having mg sin theta equals to coefficient of static friction multiplied by the weight of the box and this cos theta here. So I'm looking for this. So for me to find this, I just divide both sides by mg cos theta. Mg cos theta. When I do that, I end up having the coefficient of static friction is equal to mg sin theta divided by mg cos theta. So there's mg here, there's mg here. I divide on both sides. I end up having sin theta divided by cos theta here. This sin theta divided by cos theta, it's a mathematical thing which is just equivalent to tan theta. That's how I did it.
Alright.
Okay, let's move forward. So this is what happens when your box has refused to move. Now let's look at the case when your object says, okay, I'm going to move. If your object decides to move, and the only kind of movement which is going to do is one which is going to result in an increase in the velocity of the object. So in that case, the acceleration is not going to be equal to 0. So there's going to be a non-zero acceleration. Now, if there is acceleration, we want to know what the acceleration is. If there is acceleration which is causing the velocity of an object to increase as it is going down in this case, we want to know about it. The reason why we want to know acceleration is because for us to use our equations of motion, v is equals to u plus at, s is equals to ut plus half at squared, v squared is equals to u squared plus 2as. For you to use any of those equations, you need to know the acceleration. Without knowing what the acceleration is, you cannot use those equations of motion to predict the velocity of the object. You cannot use those equations to predict where the object is going to be at a certain amount of time, after a certain amount of time. So basically, without knowing the acceleration, you are stuck, you're in the dark, and you don't know anything. So we need to know what the acceleration is. Luckily, we have already worked out what the resultant force is along the x direction. The resultant force along the x direction, as you can see, is equals to mg sine theta minus the coefficient of friction multiplied by the normal force. Now that our mass is moving down the incline, this coefficient of friction will change to the coefficient of kinetic friction. Therefore, our resultant force will become mg sine theta minus the coefficient of kinetic friction multiplied by the normal force equals to the mass multiplied by the acceleration along the x direction. We know that the normal force is equals to mg cos theta. We already did that up there, so we substitute there. So we end up having mg sine theta minus the coefficient of kinetic friction multiplied by mg cos theta equals to the mass of the object multiplied by the acceleration. Our interest is not the resultant force. We already have the resultant force because the resultant force doesn't change. Our interest is to find the acceleration along the x direction. So we divide both sides by m. When you do that, we end up having ax is equals to mg sine theta minus mu k mg cos theta divided by m. Then we divide this side by m. So we end up with mg sine theta divided by m minus mu k mg cos theta divided by m. So when you divide m and that m goes, this m and that m, they go, you end up having this, end up having ax equals to g sine theta, then minus mu k g cos theta. So this is what you have here. Ax is equals to g sine theta minus mu k g cos theta. Now there's a g here, this side, there's a g here, that side, so you factor out the g's since the g is everywhere in both terms, so you end up having ax is equals to g open bracket sine theta minus mu k cos theta. So this is the expression which gives you precisely what the acceleration is going to be along the x-axis. Are we clear? Don't worry very much about this expression. You are going to be given this expression. So you need to know what this expression does. That this expression gives you the acceleration along the x-axis when a box is moving under its own weight along the incline. So, how can we use in what kind of circumstances can you use this expression? The first one is when you have a surface which does not have any friction. So if the surface is frictionless, does not have any friction, and how do we represent the fact that the surface does not have any friction? In that case, the coefficient of friction is equals to 0. Then this part is going to be 0 multiplied by cos theta. 0 multiplied by anything, is going to give you a 0. So this part is going to become 0. So the only thing we're going to remain with is going to be sine theta minus 0. So we're going to remain with g sine theta. So the acceleration in that case is going to be equals to g sine theta. So this is going to be the acceleration, g multiplied by sine theta. The g is not going to change. The g doesn't change because the g, as we have seen, is a result of the mass of the earth and the radius of the earth. So these two, the mass of the earth and the radius of the earth, they're not going to change. Okay. So the only thing which can change in the case of an incline is what you get from sine theta, because the angle of the incline can be changed. So the acceleration in this case, ax, depends mostly on what the angle is. Are we clear there?
We are clear, sir.
Okay.
Oh, I'm clear.
The other case is when the incline decides to say, I'm tired of being an incline, I'm going to become a flat surface. What does the incline look like? This is what the incline looks like. It makes an angle theta. So when the angle theta becomes 0, then this incline becomes a flat surface. So when the incline decides to become a flat surface, in that case, what happens to our expression of acceleration? So this expression of acceleration, when theta is equals to 0, so you end up having, here you put 0 degrees, there you put 0 degrees. So what you're going to end up having is going to be ax is equals to g sine 0 degrees minus mu k cos 0 degrees. Sine 0 degrees is 0. Cos 0 degrees is 1. So this part here, 0 will disappear. This part here, cos 0 becomes 1. So you're just going to end up with minus mu k multiplied by g. So in this case, when you have a flat surface, the acceleration is equals to minus the coefficient of kinetic friction multiplied by g. Is that clear? That is why this acceleration explains why an object which is sliding comes to a stop. We looked at a case of sliding, I think, last week, when we were working out the resultant forces, where we said if the pulling force becomes equals to 0, then the acceleration is going, if I can remember very well, then the acceleration we're looking at here? Then the acceleration is going to become equals to minus the friction force divided by the mass. Yes, minus the friction force divided by the mass. That minus friction force divided by the mass is just this thing. Because in that case, you have divided, remember friction force is mu Fn. The Fn has got m and g. So friction is mu k mg. If you divide by m at the bottom, you end up only with mu k g. So the acceleration is mu kg. In this case, when your object is sliding. Is this clear?
Yes, sir, it is clear.
The other case is when you decide to say you're going to increase the angle of the incline to 90 degrees. So when you increase your angle of the incline to 90 degrees, this incline, if you increase the angle to 90 degrees, it becomes a wall. So this incline just becomes a wall. So on a wall, if your incline becomes a wall, then you put an object there, then you make it move down. So what's going to happen to the acceleration from this case, from this expression here? So when your angle theta becomes equals to 90 degrees, so you end up having ax equals to g, then sine 90 minus mu k cos 90 degrees. Sine 90 is equals to 1. Cos 90 degrees is equals to 0. So you end up having 0 multiplied by mu k. Anything multiplied by 0 is 0. So this whole part here becomes equals to 0. Then this sine 90 is 1. So the only thing you end up having inside here is 1 minus 0, which is 1. 1 multiplied by g, which is g. So when your incline tends to an angle of 90 degrees, the acceleration in that particular case is going to be equal to the acceleration due to gravity. So your object is now going to be falling directly under the influence of gravity. So ax in that case is going to be equal to g. Are we clear?
Yes, sir.
Any questions? Are there any questions? We have come to the end. There's nothing more.
No questions, sir.
Are there any questions? Sorry? The thing really is, this formula is going to be given to you. We will give you this formula. Ax is equals to g sin theta minus mu k cos theta. So you need to understand what this formula does and how you can manipulate this formula to get what you want. Are there questions? Okay, so if there are no questions, we'll come to the end here. Hopefully we'll meet tomorrow. I'm not sure, but I'll try to make an effort because I've got things I'm trying to do running up and down. Okay, so
Right.
yes, I'll stop sharing unless people have got questions. But if there are no questions, we have been recording this lecture. We'll post it to the YouTube as usual, and the links will posted in Moodle.
So I've got a question.
Yes,
How true that we're having a test on 22nd?
Ati,
How true is it that we're having a test on the 2nd?
on the 20 what?
2nd.
22nd of May.
Yes.
Yes, apparently I've also heard a rumor that they want to give you a test before you go home. Yes, so prepare for a test towards the time you're going home.
Alright, thank you, sir.
Yeah. Any other questions? Okay, so if there are no other questions, we'll come. Joshua is left. Okay, see you tomorrow then. Okay, so I'll stop recording.